Hi, welcome to this overview of our Artefact submission. So this is for the paper Semantic Comparison of Alloy Models, and the contents of the submission are a written PDF, which is basically these slides, then a Watch Me video, which is the screencast that I'm currently recording, then a prototype, quite limited prototype of a GUI for our extension of the Alloy Analyzer, and the experiments code, and so the package binaries and the scripts to run the experiments, and also the data of the latest experiments, which are an update to what is in the paper, but I'll go over more details soon. And then the source code of our implementation, which contains the Alloy code, and then in addition a copy of some data sets. The sources of the datasets are in the paper, and then this project, Alloy Tools, Alloy Div. So that's the place where we put our code, our extension of Alloy. The platforms that we used, so we have developed the code and tested it on Windows 10 and also Ubuntu. We used Eclipse 2006 and OpenJDK 11, so OpenJDK 11 on both Windows and Ubuntu, and on Windows we used some older Eclipse, maybe a year before that, so the Eclipse mainly any kind should work. For the jar files you probably need a Java 11 or older, because we compiled them with this OpenJDK 11. And for our experiments to run them, we use this CryptoMini SAT-JNI. You can use any other SAT solver. So on Windows, we could only use the SAT4J, the Java implementation of a SAT solver, because the binaries that come with Alloy, they are only for 32-bit Java, and we didn't have a 32-bit Java on our Windows, so we ran all the experiments on Linux systems. You'll also see that they run with bash scripts, and I think we hard-coded the SAT solver in the experiments. You have all the code, so if you really want to, you can change that, but yeah, maybe just go for Linux if you want to run the experiments. But the prototype, we built it with Alloy's build script, so the GUI, this should run on Windows and Linux, and you can select the SAT solver in the GUI there. So the suggested steps to go through are: quickly browse the README PDF. Really do this only quickly, because the stuff is kind of repeated in the Watch Me video. As you see, we're going over this README. And then you can play with the GUI prototype and also inspect maybe the scripts that we used for the experiments. And finally, you can also inspect the code if you want. So we start with the Alloy GUI prototype. I'll run it from our Eclipse, so basically all the projects, they're Eclipse projects. You can just double click on the jar file or run it using Java jar and then the GUI name. Then you can load or create some Alloy models. So what we'll do is we'll use the ones of the paper. So in the paper we have this version 1 here, and then a version 2 and a version 3 and some story how they were created. So 1 was the base, and then it was modified by 2 members of the team independently to these 2 different versions. So let's run it from the source. So our code is implemented in div, in this org Alloy Tools Alloy div. All the other projects here, they are from the Alloy Tools repository. And let's see, where's the GUI? So the GUI is here. Let's just run the GUI. And then we can open this paper version 2, we need that. Then we have the version 3, and version 1 would be nice. Oof. So the code is in Alloy div misc paper. These are the example models. There's tons of Alloy models with this artifact. So this is the example, you can just run it as usual, see an instance. Maybe that's the instance shown in the paper, not sure. So basically there was an issue with this. We could have two requests that come from the same endpoint. Requests that come from, well, we have some that come from different endpoints. Let's see. Yeah, so for example, here we see two requests that come from the same endpoint, and this was basically what the team wanted to avoid. So that's why they extended it, for example, here, where it says that our login request has exactly one target, but then they also extended it in a different way, quite differently. So now let's see if we can compare maybe version 1 and 2. We should see that there is a difference. So in the paper example, we said that the change is a refinement. I think the semantics of the yeah, so version 2 should be a refinement of version 1. This means that there should not be any new instances that version 2 contributes. So let's have a look. We click the new button, compare, run a semantic difference. So we want to find instances in version 2. We're now looking for new ones to check that it's really a refinement. So if there is an instance in version 2 that is not in version 1, then we wouldn't have a refinement. So let's check. It says unsatisfiable. That's very good. So we have a refinement. Now let's see the other way. Sorry, it always goes back to the default. So now we will look at version 1 and see if there's anything that was in version 1 and not in version 2. So these should be the instances that the team wanted to remove. And yes, they wanted to remove some. Let's see what's the problem with these. Whoop. Okay, yes, so it says here that every endpoint should make at most one login request to exactly one endpoint. So in these examples, they don't have the two. So they, or here maybe, do we have multiple froms? So it's also forbidden that the from an endpoint, the login request, I think then we need to have, it needs to be the same, identical login request. So from every endpoint, there should only be one login request, and here we have two. So basically the bad things that were described here, that, yeah, two login requests from the same endpoint, that's also now forbidden in the new version. So these were all the instances removed. So we have kind of confirmed the refinement and we saw some of the instances removed. Now we might also want to check about the common instances. So did we preserve the good stuff? So why do we have more windows open? So now we can compare again version 1 and 2, and we want to see any common instances. So now they should go from, the login request should go from one endpoint to one endpoint always, and never from the same. That's a complicated one. So they all go, no login requests go from the same endpoint, and each one has one that they are requesting from. Okay. Again, not a single login request, that's also fine. Okay, so now we have the common instances here are the good ones. And finally, we wanted to see, Here they discovered that version 2 and version 3 have equivalent semantics. So version 2 is this one here, where we count the 2, and then we have this very nice fact here, whereas version 3 is a bit more lean in terms of how it expresses. So if we see the instance calculation here has 250 variables. Here, if we execute it, it's 260. So there's some difference, but we can check whether the semantics are the same. So let's do equivalence of version 2 and 3. And then if we analyze, we see that it says the models are equivalent. So now just to demo that it really works, and not just always says equivalent. So let's take 2 that are not equivalent. We check that there is a difference between 1 and 2, and if we say that 3 and 2 are equivalent, then there should be no equivalence between 3 and 1. So we say analyze. Okay, we don't see the console. It basically says they're not equivalent, and then it shows us a counterexample. So here is a counterexample of an instance that is only possible in one of them, demonstrating that it's not equivalent. So this is an instance that's only valid in version 1 because it doesn't have the 2 for the login request. Okay, so that's the prototype. You can play with any other, even the sample models of Alloy. The important thing is to use this compare button here. You need to have the file saved, and it will not ask you if you want to save it. So for example, if you have this new thing, and then it just won't show up here if you have a file that's not saved. And if you make changes here that you don't save, then this thing will ignore it and only take the last version from the file that you saved. So yeah, that's quit. Okay, that was the prototype. Now the GUI prototype. Now the experiments, they are in the experiments folder, and what you see is there is a binary called diffjar, and this is how you can use it. You can run it with Java, and you give it one Alloy model, another Alloy model, then a scope, and then you say whether it's with the predicate or not. If it has 4 parameters, it always takes the predicate of the run command into account. So that's one of the extensions, I think 7.1, that we implemented to take the predicates of the run command into account. So it will check whether it will basically run a semantic diff and check whether there's an instance, and then it will print out the information of whether it found an instance or not in a CSV file. So this way we can run our experiments. So this is the jar file. The results are all here. We can have a look what these experiments look like. Okay. It's a CSV file, and it basically prints the first version, second version that you gave it as arguments, then the number of variables in the SAT problem, then the time in milliseconds that it took to analyze, and then whether it was true or false, whether it found a semantic difference or not. So it basically doesn't matter whether it's true or false, because here we're just checking for performance. There's no wrong or right. We run it for different scopes. So you see the scope parameter 3. For each different scope, we have a diff file, a CSV file. So let's look at maybe the one for 38 might be incomplete because this really takes ages to complete. Yeah. So this is the data, and then there are scripts to create this data. So there's this diff shell script, which is this one. and it basically has only this one line that is important. We run a timeout of 10 minutes for then we measure the memory consumption of this execution of the jar file, and that execution is exactly that which was on the previous slide. We also store a memory log that's not reported in the paper, but you can have a look anyways. The memory logs are also there. I think the highest that it ever goes for the diff, usually it's just, I don't know, for the simple diffs it's like 130 megabytes. I think the highest was maybe 6 gigabytes, but that's for very high scopes then. So this file, this run command is basically using the diff. Then you can, if you want, for the comparison that's reported in the paper, you can use this line, which is then running the version 1. So it only takes the first file and basically runs the default alloy calculation without running any of our code. This is just for comparison as reported in our evaluation. So this stuff with the timeout and the memory consumption measurement is then run by the second run all. So the run all is also described here. Basically lists these 836 pairs of specifications per scope and runs from scope 3 to scope 58. So here it starts everything with scope 3 and the different pairs of specs. Goes all the way to 58. That's, yeah, something like 10,000 10,000 diffs. And the thing is, if you want to run all this, it will take a few days on a strong computer, just a single iteration of this. And it will, I think, I'm quite sure that it uses the hard-coded SAT solver crypto minisat. So it's basically this code here, the diff stats computer, which somewhere on Windows it would automatically use SAT4j, and if it's not on Windows it will use crypto minisat. That's somewhere deep inside this diff command. Okay. That's if you want to rerun the experiments. The experiments here, reported here and described here, and that you have the code for, are no longer the ones in the paper. So we're going to revise. So I mean, this stuff is still true because that's the size of the specs and everything. But the analysis cost, we're now running a different one. So this one was basically running without the run commands, and we only had the run commands in somewhere extension 6.1. So this is now fully implemented and tested. So we're now using that as default. It just makes more sense because there were many examples, like the address book examples of the alloy book. They were only different in the predicates that were in the run commands. So that's why it's probably much more meaningful to take the run commands of alloy into account. So we have to recalculate all these because these were based simply on everything without run commands. So it simply ignored the run commands. It only took the signatures and facts as we describe here in the paper. But so the stuff you see in the CSV files will probably give some different numbers here. And yeah, so that's it for the experiments. Now some little tracing of the code to the paper, because you're probably not going to look at all the code, but you might look at the paper and see, oh, where is this stuff in the code? So we already saw the section 2 examples, the alloy listings. They are in this MISC folder under paper. There are 3 alloy listings. That's the ones that we saw in the demo. Then the paper contains a few algorithms, and the algorithms look hopefully very nice because they're just pseudocode. We need to merge the signatures, and the signature merge, this is basically the algorithm 1, and then this takes place in this method. So if we go to the module merger, then we can see where algorithm 1 takes place and what algorithm 1 really looks like. So the module, no, that's the test cases. Module merger, and then yeah, this basically gets all reachable signatures from the alloy models, and then starts to merge them. There are many steps for that. We also compute inheritance information on the signatures. Then we do merging of the subset signatures. So above was the primitive signatures, which have the regular extends inheritance, and then the subset signatures, which have this inheritance, also described in the paper. And then this basically also we need to build the inheritance for the field expression, stuff like that. So that's algorithm 1. Then let's go back. Algorithm 2, the merging of fields of common signatures. This is no longer in a single place. There are basically kind of 2 places. So again, in the paper, the algorithm looks very nice, and we have these kind of 2 cases for fields with the same name. So that's common fields of 2 signatures. And then we have unique fields, and that's implemented in 2 different methods. So the one for common fields, that's this merge field. So if you want to have a look there, that's this method here. And yeah, what looks like one line in the pseudocode is actually quite a few lines here, because we have to check whether what kind of expression types are used in the field declarations, and take them apart, then translate them to the new merged signatures, and then put them back together. So this is for the common ones, and then there is a similar code for the unique fields, where we also need to adapt the field multiplicities, because we need to make them, we need to have the possibility to make them optional and basically suppress them in the other module. So yeah, this stuff here, this suppressing in the other module, this basically says this field doesn't exist. These are not called CV1 and CV2, they're just called C1 and C2 in the code. But yeah, other than that, it's very similar. Algorithm 3, computing the inheritance of fields and signature references. That's we do in the constructor of the inheritance util. That's here. That basically computes the transitive closure of the fields that you might inherit from other signatures. And then another interesting one, this is algorithm 4, this translation of the expression here. So basically the translation of expressions that come from one of the source modules to make them valid in the common module. This is this. There are a few methods of this name that basically just wrap this one method. So I'll just go over that because it's quite similar to the pseudocode, but in the end very different, much more complicated. So this is the pseudocode. Basically, if we have a constant or a unary expression, then simply do these simple things. If we have a unary expression, then do that. So for some like primitive signatures, we have to look it up. But basically, yeah, expression lists, quantified expressions, we have translations for all these. Constants are the most simple ones. expression calls, let expressions, stuff like that. So that's this algorithm 4. Then this extension of the run and check command and the scope computation. So this is in the paper the extension that was so far not evaluated, but it's much more probably makes a lot more sense to evaluate this because people use run commands and check commands to check specific things about their alloy models. So that's why now we're going to change the evaluation to run that. And for this, we need to take into account user-defined scopes. And that's not so trivial. Also, it has to handle the scopes of inheritance. So we are flattening inheritance, but the original scope computation for subsignatures and stuff, we have to add that by adding some manual constraints to the multiplicities of the classes of the signatures, and that happens in the command generator, generate diff command. So our command generator, generate diff command, starts by calculating for the desired scope the different scopes in the original module, in a module that would only have the desired scope, and then we do some maximum and minimum computations to make sure we end up with correct scopes. So and add these constraints where we count. So the cardinality of some union of signatures will be set to either the scope in the original or overriding it if we have singleton signatures. There are quite a few rules in Alloy on scope computation, and we mainly rely on the scopes computed by Alloy's own scope computer that we wrap in this MyScope computer. But that's basically this extension in 6.1. Quite technical. Now the implementation and evaluation. So the jar files that you saw, they are basically generated from this diffstats computer and diffstats computer 1, where this is going into the diff.jar and this is going into the v1.jar. Then another interesting thing is, there are quite a few tests, and then in the validation section, we describe how we basically compute the difference of two modules and then check that the difference is really an instance of the second module, because it has to be. So this way we kind of validate our implementation, and that stuff is done in that code is done in the module comparison test. Module comparison test that basically runs again over, I think, 600 pairs of models, and then computes the difference, and for the difference for each it computes 10 solutions, and then afterwards it checks every single solution whether it really is an instance of the second model that we were checking. You might see, so some of these test cases, they crash with errors. That's because there are some known limitations. So we list these limitations in the paper. The limitations, yes, one of them is field arities, but I think that never happens. Then another one is higher order quantification. That might happen because Alloy supports only very limited higher order quantification. But if we negate that, it usually doesn't support it anymore. So that's why we also filter out that. Ordering is currently not supported. So you see some test cases, they filter out the ordering exception, the higher order quantification exception, something about importing integers, or that's some issues in some of the models for evaluation, or that some imported files cannot be found by the Alloy parser. So these are not our problems. This already happens when Alloy parses something. And we don't filter out these exceptions always. So sometimes you have exceptions in the test cases, and then if they are of this kind, then everything is fine, although the tests are not green. But these are known limitations. Okay. Yeah, but the validation should run without problems. Okay. Then this was a quick overview of the code as it appears in the paper, and where to find all the different implementation pieces. Then finally to what kind of badges we're applying. So badge 1, availability. Yes, we made it available during the review process, and we're also happy after it has been reviewed and for the final version of the paper, for the camera ready version of the paper, to place the artifact in the university's Figshare repository. So I think Figshare is one of the commercial repositories that is allowed by the ACM, where we get a DOI and everything, after we have maybe incorporated some feedback from the artifact evaluation. Then we would also apply for the reusable one. So yeah, documentation. So we see this video and walkthrough and the paper and the relation between the paper and this as some documentation of the code. There's also some Javadoc in the code. There are test cases. Yeah, and those are the two badges that we would apply for. Thank you.